Okay, welcome back to Physics 209. This lecture, we're going to talk about motion in one dimension. All right, so as we discussed already, there's a difference between vector quantities and scalar quantities. Quantities. Okay, so in particular, vectors have magnitude, which is how large something is, and direction, and scalars, which are numbers, just have magnitude, no direction. Right. So, in what we're going to talk about now, there's going to be two new quantities. So, first one is going to be displacement. Right? This is a vector quantity. Right? And basically tells you how position has changed. Right? So it's usually basically tell you how large it is, and then basically how in what direction the position change. And the other one is distance. Right? Really, distance traveled. This is a scalar quantity. And I'm going to write down what it is. Basically, it's just really the distance traveled, right? Okay. So, for instance, you can imagine two possibilities here. Let's imagine basically these two vectors are the same length. Draw it the same way, right? This is going to A to B or B prime, okay? And these vectors are the same same length, right? So in the case if I ask what's my distance travel going from A to B or A to B prime, it would be the same distance travel. So it's going to be same distance travel, or just distance for short, okay? But different displacement. Why? Because they're in different directions. Okay, now we're going to talk about motion in one dimension in this case. So in one dimension, this direction is represented, by the sign. Okay. So either this goes in the plus direction or the minus direction in that case. Alrighty. Now, just give a quick example. That means imagine you have a line here. This is plus x direction, right? And imagine you start here. This is xi, and there are two positives, xf and xf prime. Okay. So in the first case, like if you basically move to xf, then basically xf is greater than xi, which implies that delta x, which is always xf minus xi, this has to be greater than 0. So that's the sign of the direction, it's in the plus x direction. On the other hand, xf, which is prime, which is less than xi, that implies in this case delta x, which is xf prime minus xi, that's less than 0. So basically tells you that you're moving in the minus x direction, right? Okay, so that's great, right? So, just think about how I want to do this. Right, okay. So I did this example in class, right? Where basically, if you're moving Imagine you have like 4 clicks. So this is like this is 0, 1, 2, 3. All right, and suppose you're moving basically 3 steps in one direction. All right, 1, 2, 3, and then you move back 1, 2 steps in that direction. All right, then in that case, basically, your xi was here, your xf is here. You might say that the displacement is equal to xf minus xi. That's just basically plus 1, right? Okay. Now, suppose, however, it took me basically a time, which is 5 seconds to traverse this distance, right? Okay. Right, and we're going to call these meters, for instance, right? So this is basically plus 1 meter, okay? But then the distance traveled, oops, that's just going to be the total distance. So this I went 1, 2, 3, 4, 5. So this would be 5 meters, right? Okay. It's just that I backtrack on myself. So basically, I get different distance travel versus displacement. Now, if I tell you that this thing took me 5 seconds altogether to go, all right, I can basically define 2 new things, which one is the average velocity, average speed versus average velocity. So the average speed in this case, this is going to be the distance traveled over the time. And I just figured this out. This is basically 5 meters over 5 seconds. That's just 1 meter per second. Now the average velocity right? This is going to be delta x, the displacement over the time. Right? This is displacement. Okay. This is just going to be 1 meter plus 1 meter over time, which is 5 seconds. That's just 0.2 meters per second. And then this one will be to the right. Okay? You could write that down just to indicate the direction, but the fact that it's plus basically should tell you that already. Okay. Now, so that means the average speed. This is a scalar quantity, and this is a vector quantity. All right? This will become important in a bit. Okay. Now in class, I basically did this example of a goalie and a puck and stuff like that to show different velocities and whatnot, right? And maybe I'll try that again this time, but I'll use a simple one, all right? So let's imagine, this is a simple example here, okay? Let's imagine I travel, I walk like 1,000 meters to my car, right? And then I drive back at 50 meters per second, and the total walk plus drive time is let's see, let's make it 300 seconds. All right. Let me think about this. Let's make it. I want to make a simple number here. Let's make this thing 520 seconds. All right. Okay. How fast I walk? Okay. All right. So this is a very useful problem to do. All right. So let's basically, I'm going to show how to solve this problem using a 5-step process. All right, so let's list the 5 steps first, and then we'll go. So define what you need. Okay. and I'll give it some space here, and then basically define what you know. I'll try to slow down, write a little neater here. Okay. Number 3, draw out. I'll leave a little space here. Okay. Number 4. Let's see, what's this? This is like, once you draw out, what you want to do is better set up problem now. Okay, so there's a bit of work before you set up the problem. And then number 5 is, we're giving a lot of space now, so we'll go back in a second. Number 5 is basically remind yourself what you want, solve for what you don't need. Okay, this last step will become clear in just a second. All right, so let's define what I want. So what do I want? All right, so let's see. So let's call this variable time t here. We'll call well, there'll be a few things. This will be basically v drive. Okay, so we'll define what I need. So I want v walking. Okay, v walking. Okay, define what I know. Well, I know a few things. I know basically v drive, right? So I'm driving back, right? So let's imagine that I should draw out first. Okay, this is my car. Okay, this is 1,000 meters away. This is me. I'm gonna go here. I'm gonna drive back VD at some velocity, which is given right here, 50 meters per second. So so this VD is gonna be minus 50 meters per second. So that's basically what I know already. That's one thing I know. I also know total time, T final, is basically 520 seconds. Right, so that's what I know. All right. Okay, great. Okay, so that's what I know. And now I know one more thing, which is the total distance, delta x, is just going to be 1,000 meters. Right, so those are 3 things I know. Right, and so from this, I can basically say that this is, this delta x is 1,000 meters. So let's draw out. That's the situation. All right. And now let's set up the problem. So at t equals 0, I basically start walking towards it. So t equals 0, walk to car. Okay, t equals, now at some time we reach a t prime, sometime t prime. T prime, start driving. And then finally at basically t equals, I'll call this t final here. T final, which is 520 seconds, basically this is basically arrive. Okay, all right, so once I have this thing, all right, I can sort of set things up. So basically from going here to here, all right, I know delta x is equal to 1,000 meters. That's going to be equal to basically the time it takes me to walk, v walk, times the time it took, which is t prime minus t initial, which is 0. Okay, so v walk times t prime. Okay, that's what I know. The second thing I know is that basically starting back from here to there, right, I basically have to move back 1,000 minus 1,000 meters, so I'm moving backwards now. That's going to be equal to VD, which is minus 50 meters, okay, times the time, which is TF minus T prime, right? Okay, so let's just write this thing out. That's minus 50. TF is 520 minus T prime. Okay, so that sets it up. Okay, so now remind myself what I want. So I want, let's say I want VW. That's what I want. What don't I need? Okay, I don't need T prime. So I'm going to solve for T prime first, right? So look at this one. This is going to be 1,000 here. So I'm going to basically let T prime equals 1,000 over VW. That should define VW on this top side here. I'll take this now because I don't want this thing. I'll plug it into here, right? So then what I have is now minus 1,000 equal to, so let's see, let's make it all plus now, 50, 520, right, minus 1,000 over VW. Okay? All right. So let's just basically, this is just math now, right? So this is going to be equal to, this times that. What is that thing? That's just something nasty. Let's just plug in numbers here. Make it simple here. Okay, so let's see. 50 times 520. What is that thing right there? Well, let's get the, okay, that's 2.6 times 10 to the 4. Okay, 26 thousand. Yes, 26,000. All right, this 1,000 here is equal to. Now this is going to be minus 50,000 over VW. Okay, so what I get here, subtracting this side, that's minus 25,000 is equal to minus 50,000 over VW. So VW goes up here, minus 25,000 goes down here. 50,000 divided by 25,000 is 2, all right? So VW is equal to 2 meters per second. And that's it, basically, right? So 5-step process. Define what I want, define what I need, tell me what I know, draw it out, set up the problem, and then the last trick is that I gotta remind myself what I want and solve what I don't need, which case was T prime, right? And if you do that, basically, you can solve a lot of these sorts of problems that involve multiple variables, right? Okay, that's beautiful. All right, so now let's talk about, let's talk about instantaneous velocity. So we haven't talked about this yet, okay? Instantaneous velocity. All right. Now, so we gotta recall velocity is basically some displacement over some time interval. So this is basically displacement over some time interval, right? And what we want to think about basically is, now suppose that you're just walking along at a constant velocity, right? Then you're gonna have some displacement over some time, right? Depending on what the time is, right? So let's say you're moving at 5 meters a second, you have a displacement of 5 meters basically after 1 second, 10 meters after 2 seconds. But let's suppose you go the opposite. After half a second, you have 2.5. After a quarter of a second, you will have a 1.25 meters, right? And you keep going down further and further, right? So what happens if the time interval goes down to nearly 0? Well, in that case, basically your displacement also 0, and so roughly speaking, this will just be some 0 displacement over some 0 time interval, okay? Now that doesn't make sense, right? This doesn't make sense. Right? And so basically for this stuff to start making sense, you have to basically define calculus. So let's enter calculus. So use right? And the way it works is that basically, let's imagine that if I throw, let me think about this. If I throw something high in the air, right? So let's imagine I'm me, and I throw a piece of chalk up in the air like this, right? So what's gonna happen to this chalk? The chalk's gonna go up, it's gonna stop, and it's come back down again. That's what's gonna happen to the chalk, all right? Okay. Now, if I plot this thing as a function of time, okay, I define my y-axis this way, say. So y is here, time is here. At time t equals 0, this is y equals 0. It starts at 0, but then I throw it, right? and it goes up, 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 and eventually hits a highest point, and it comes back down again. All right, and then at some point I catch it, basically sometime in the future. Right? Okay. Now, if I ask myself, what is the displacement for two different times? Let's say this was t1, and say this is t2, right? Then this here is delta t. This here is delta y, right? Now, the idea behind calculus is to bring these 2 points closer and closer. So if I bring it closer like this, right, then this is my new delta y here. And if I bring it ever closer, eventually what will happen is that they'll be right next to it, infinitesimally close to each other, right, in this case, okay? And then you can define a velocity, because it's not exactly 0 now, right? It's just very close to 0, right? So if I bring these bring the 2 times, infinitesimally close to each other, right? Then I can define Vy is equal to the limit as delta t goes to 0, right? That's the bringing them really closer. Delta y over delta t, okay? This is going to be dy dt. This is the derivative. Okay, all right. Okay, so this is the operational derivative, and in your calculus class, you learn how to take derivative of many different things, right? So, so in calculus class, you learn to take many derivatives. Okay. But one of the most useful ones is just this following one, okay? So let's learn one. But the useful one here is for df dt, where f is equal to some constant t to the n power, right? This gives me basically df dt, which is dc t to the n dt. That's just nc t to the n minus 1, right? Okay, so that's basically this key result here, which we're going to use many times, right? So before we move on, let's basically do a quick example so we don't mess this up, right? So let's do a quick example. The example is basically, suppose a car moves like, okay, so x is a function of t is equal to v times t, right? Okay, this v is constant. All right, what is an instantaneous velocity? Okay. All right. So you could still, so in that case, basically, you could use the same thing that we just asked earlier, right? Which is the 5-step process, like define what I want, define what I know, right? And let's draw all the stuff. I'm just these two, and then we're gonna see basically what we need. So define what I want basically v of the car, okay? Okay. Define what I know. What I know basically x of t is equal to v times t, right? So I can just now do it, right? Remember, the velocity is just that. So v of c is equal to dx dt, right? And so this is basically d by dt of vt, right? So this is t to the 1 technically, right? And so this is going to be 1 times v, v is a constant, times t to the 1 minus 1 is t to 0, which is just 1. So just simply equal to v in that case. All right? Okay. Beautiful. Alrighty. So we need a few more rules of derivatives that will be useful. Okay, so the first one is that they're linear. And so basically d by dt of f of t plus g of t, that's just basically df dt plus dg dt. Okay, so basically it goes right through the these additives here. Okay. Likewise, if you have basically d by dt of c of f of t, where this is some constant, that's just going to be equal to basically c times df dt. Okay, so that goes under linear. Right. Second thing, useful, chain rule. Okay, so in this case, basically, if I have d of f, f is a function of x itself is a function of t here, well, dt, that's just going to be equal to df, take the derivative with respect to x, then take the derivative respect to of x with respect to t. Okay. Final thing, product rule. Okay. So I want to take d by dt of f times g. So multiply these. This is just simply going to be df dt times g plus f dg dt. Right? That's the product rule. Okay. All right. So suppose I consider the problem of throwing the chalk in the air again. Right? So suppose if I throw chalk in the air, at 10 meters per second, right? Okay. It turns out I can approximate motion y is equal to 10 times t minus 5 t squared. Okay. You'll see why this is actually later on, but for now, just take it as face value. Okay. So what is its instantaneous velocity? Okay. So what is it? I need v. Okay. And you sort of know how to do this, right? I know y of t, which is that thing right there. And so this is solve basically. V is equal to dy dt, d by dt of 10t minus 5t squared, right? And then all of a sudden I have the final value already. 10t, that's just going to be 10 minus d by dt of minus 5t squared. That's just going to be, bring the 2 down. 2 times 5 is 10 times t to 2 minus 1 is just t, right? And that is instantaneous velocity in that case. Okay, awesome. All right, so we have that. We have a velocity now. Let's see. Well, let's have it go through. All right. Okay. So the next thing I want to talk a little about, maybe I'll just skip starting the page. No, just not starting the page. Is acceleration. All right. So now suppose I make a similar plot here. Function of time, but now rather than putting the position, I'll put the velocity of this thing. All right, and the velocity of this thing can be a lot of different things. All right, and I'm gonna pick basically 2 points in time here, right? T1, T2, and this becomes V1, V2. And as I bring these times close to each other, T2 bring it close to T1, all right, I can define, so as I bring T2 close to T1, I can define dV dt is the limit as delta t goes to 0 of delta v over delta t. Okay, so this we define as a is the acceleration. Okay. Okay. Actually, it's not the acceleration; it's the instantaneous acceleration. Right. If I kept them far apart, basically, if I basically define a average, this might just be basically delta v over delta t. This is here the average acceleration. Okay, so the instantaneous acceleration is simply the average acceleration if I take the time interval to be nearly 0 in that case. All right. Now, what's cool about this? This is the acceleration, is change in velocity or change in time, and recall that the velocity is just the instantaneous velocity is basically d x dt. Okay, right? And so this just that implies that a is equal to d by dt of v is d by dt of dx by dt. That's just d squared x dt squared. So this is what's called the second derivative. Second derivative of the position fact. Okay, all right. Okay, so let's first consider how I want to say this. Okay, let's first consider the following. Okay, so let's consider a case for constant acceleration. All right. Well, in that case, what do we have? We basically have delta v over delta t. And in that case, if it's constant acceleration, average acceleration, and instantaneous are the same thing. All right. That's just going to be a, some constant, right? That implies that delta v is just simply a times delta t, right? Now, if we choose t1 equals 0, t2 equals final time, right? v1 equals v initial, v2 equals v final, right? What that means is that basically the final velocity is simply equal to the initial velocity plus ATF, right? It's actually ATF minus TI but ti is 0 in that case, right? This is the first important equation we need. Okay? We also have, say without proof, we'll prove this later, the final position is going to be equal to the initial position plus the initial velocity times the final time plus 1/2 ATF squared, right? Another way of writing this is delta x is equal to VI delta t plus 1/2 A delta t squared, all right? Put that parenthesis there so it becomes clear what I'm actually squaring. Okay. Now, one thing you might notice is that basically, I'll like this is equation 2 here, is that here I have the final times, all right? And sometimes I don't care about the final times, right? So I may just basically want, for instance, I might just want the position, for instance, right? So you can come up with another equation, solve for what I don't want. So basically, from 1, this gives me what TF is. TF is equal to VF minus VI over A, right? I'll plug it in 2, plug it in here basically. All right, so in that case, if I do that, I get something that is not so bad. So let's see, so let's just write like this. XF minus XI, I'll leave like that, is equal to VI. Now TF is this thing, VF minus VI over A, okay, plus 1/2 ACE times TF squared, that's VF minus VI, entire thing squared now, over A, right? Okay, so let's see, if I do that, squared, sorry, it kills off 1A, and now there's some trickery here, all right, which is not a priori obvious that this actually turns to be true, but if you actually multiply this thing out, what you end up getting is you end up flipping, let's see if I remember this correctly, you end up flipping the sign of this thing, so you end up getting this is actually equal to 1 over 2A, right? This is VF squared minus VI squared. Okay, so I'll let you show that for yourself, that in fact is the case, right? Which gives me the third equation now, if I multiply 2A on both sides, 2A times XF minus XI is equal to VF squared minus VI squared. Okay, so that's equation number 3. That would become important later on, right? Okay, so this equation number 3 is actually quite useful in a lot of contexts, right? So let's imagine I have, like for instance, like the following problem, okay? So a car moves at 30 meters a second, right? And then I'm stopping at -6 is my deceleration, -6 meters per second squared, okay? All right, the first question is how much time to stop, okay? Second part of the question, how far? Okay. All right, so let's basically do this thing. All right, so how much time to stop? That's not so bad. Basically, we figure this out, right? So VF is equal to 0. VI is equal to 30 meters per second. Acceleration is equal to -6 meters per second squared, right? And then I want to find TF. Okay, so basically equals question mark. So number 1, what I want, that's TF. Number 2, what I know, well, that's VF, VI, A, right? Okay. Number 3, let's draw the problem out. Here's my car. It's going to be stopping, right? After some time. TF, and at some position, XF. Okay? I'll just call this basically TXI equals 0, TI equals 0, right? So start at that point, basically. Okay? All right. Well, before I can now proceed to solve this first part here, how much time does it take to stop? Well, let's see. That's just delta V, which is VF minus VI, is equal to A times delta T. That's just A times TF minus TI. Well, TI is 0, so that's good. All right. A is minus 6. That's good. All right. And what is that I want? Basically, at XF, I know this is 0. So 0 is equal minus, what is it, 30 meters per second is equal to minus 6 times TF. So that's easy enough right there. Minus 30 divided by minus 6, that's just TF is equal to 5 seconds. All right, beautiful. So I can nail the first one, right? Now, for the second part, how far do I go? Well, that's not so bad either. I can figure this out. So XF is equal to XI plus VI T final plus 1/2 ATF final squared, right? So XI was basically 0 plus V at I is 30 meters per second times TF, which is 5 seconds, plus 1/2, what's this, is minus 6. TF is 5 squared. Okay, so let's basically go through all this, right? So that's plus 150, plus, now this is 6 times 25, that's 150, I think it's 75, minus 75. Right, so I have 75 meters for this one, okay? Now, sometimes you're not asked the first part. You might just want to know how far it is in this case, right? So what I want in this case, I want XF. What I know is the same thing as I knew before, right? If I set this up, I'm going to solve it a different way. So let's do number 4 here. I want to basically solve it using this 2A XF minus XI is equal to VF squared minus VI squared, okay? So that might seem a little more tricky, but that actually turns out to be very easy. Let's basically do this right here now. So this is going to be 2 times minus 6 times, basically, XF is something I do not know. I'm going to find out. XI is 0. That's good. It's equal to VF squared. VF at the end is 0 squared minus VI is basically 30 squared. That's 900. So it's basically 900 divided by 12. That's about 75. In this case, XF equals 75 meters again. Okay? Okay, so 2 equivalent ways of doing this. The second method is superior, where you don't have to think about what the time has to be. Okay. All right. So, let's see. Right. Let me see. Okay. So let's talk about. Well, this is equipment, so I may have skipped that part here. We'll cover it in class though. But. Okay, let's do one complicated example here, right? Okay, so let's imagine a car moving, at 190 kilometers per hour. Okay, and it's going to be behind a car moving at 125 kilometers per hour. Okay. Okay. So now both slam on the brakes, hit brakes, and have acceleration of -6 meters per second squared. Okay, so that's my acceleration at the same time. Okay. Okay. Now I need to A, show they collide. Okay. B, at what time does it collide? Okay. All right, so let's do that first. Okay, so for part A, okay, I know my initial velocity is 190 kilometers per hour, okay? And then that's for car 1. The initial velocity of car 2, which is in front of it, is 125 kilometers per hour, right? Which I have to basically convert this to meters per second. So let's convert this to meters per second first. So the trick is, it's 190 kilometers per hour. So 190 x 1 to the 3, that's the number of meters I can travel in an hour. Divide this by the number of seconds an hour. That's 60 times 60 is 3,600. Okay, so this is about 52.8 meters per second. Okay, this one is similar. I'm not going to go through the numbers, so I'll write in my notes. This is 34.7 meters per second. Okay, now let's draw out the situation here to help make it illustrate a little better. So this is at ti equals 0. I'm going to put car 1 here. It's car 1. This is moving at a velocity vi1, com 1. And then this is car 2 right here. Okay. I will call this xi equals 0. In this case, this one's at 100, so xi of 2 equals 100. Okay. Xi of 1 equals 0. Right. It's 100 meters ahead of me. Right. Okay. And now both of these things are decelerate, all right? So I'm going to write down this one, xi of 2 is equal to 100, and xi of 1 is equal to 0, right? So I define my 0 right there, just to make things simple. All right. Okay, so first I got to show that they collide, all right? So to do that, I'll figure out basically when did they stop? How far away did they stop, okay? So let's go figure that out. So let's see. So basically, I'm going to use the following formula. So this is 2a delta x is equal to vf squared minus vi squared. All right. I'll do it for car 1. I'll do it for car 2 here. All right. So I'm going to use that thing. So this is 2a. That's basically 2 times minus 6. Right. X delta x is basically xf minus xi, right? So that's just going to be xf is going to be something I need to figure out, minus xi, that's 0 for car 1, right? Okay. And if I go through this again, hold on, is equal to now, xf is 0 when it stops, that's 0 squared, minus xi, let's see, that's 52.8. Okay, so let's go ahead and do that number there. So 52.8, square this thing, right? And then it's going to be divided, equals something. And I'm going to divide this by 12. All right, so this xf is equal to 232 meters. All right, so for car 2, that is 2 times minus 6 again. XF is something I need to figure out for car 2, car 1, minus XI at car 1, well that's just basically 100 meters, okay? That's going to be equal to, the final velocity thing is going to be 0, minus 34.7 squared, okay? So let's go ahead and figure this out now. Okay, so this is 34.7, square this thing, good. All right, and divide by 12. Okay, and I have to add 100 to it, plus 100. So in this case, XF2, that's going to be, wait, hold on, I screwed up something. Wait, let's make sure that's right. 34.7 squared, okay, divide by 12. Yes, right, add 100 to that. Perfect. This is 200.3 meters, so 200 meters. So you see that this car was in front, this car's in the back. By the time this thing stopped, this will stop at XF equals 200 meters. Okay, that's car 2 now. And car 1 will stop sometime past that at 232. So at some point, car 1 has to collide with car 2. All right. Okay. So now we have to figure out basically at what time do they collide. Okay. So to do that, we have to set up two equations here. So x1f is equal to x1i plus v1i t plus 1/2 a t squared. So this is true no matter what. Okay. x2f is equal to x2i plus v2i times t plus 1/2 a t squared. Okay. So these two equations are always true for all time. Okay. But at the time of collision, x1f and x2f have to be equal to each other. All right, so that's the key. Okay, so at time of collision, when they collide, these things will be equal to it because that's what a collision is, right? So now we can then go ahead and plug in the terms for this thing. We'll write out more explicitly first. x1i plus v1i time of collision plus 1/2 a tc squared. This is we're saying a on both sides. That makes life a little simpler. Is equal to x2i plus v2i times t collision plus 1/2 a tc time collision squared. Now, what's nice about this? These two terms are exactly the same. So now we're just left with something pretty simple now. So x1i, that was 0, plus 52.8 tc, that's equal to x2 is 100 plus 34.7 tc. Okay, so we can solve for tc now. I'll just solve per se. It's 52.8, okay, minus 34.7. We'll invert that thing right now. Let's see, invert that thing, and then multiply times 100. All right, TC equals 5.5 seconds. Okay. All right, that's nice. Okay, so all right. Okay. So we learned about derivatives. Now let's learn about integration. Okay. So So the equations one 2 that I stated earlier can be derived from calculus. Right? Right, so to do this, we have to introduce the integral. Right? Now, the thing you want to do, right, is the following. Okay? So let's imagine you have some curve here as a function of x. So that's my curve here. And I want to find the area under the curve, right? So how do I do that? So if I divide up the curve into little rectangles, say, I can add them up basically, right? So I can sum up this rectangle here, has some width about it, delta x, and has some height y. Okay? So basically the area, delta A, is just y times delta x. If I sum over all the delta a's, area, then I'm going to get something that looks like basically sum over y times delta x. Okay? Now, if I take the limit now of delta x goes to 0, right? Then basically this limit of delta x going to 0 of the sum of y delta x, that becomes this curly symbol, integral of y of x dx, right? And this is the integral. Okay. All right, so far so good, right? So what does that have to do with anything, right? So there's something called the fundamental theorem of calculus. And this is how it works, right? So, if I take a derivative, d by dx, of an integral, okay, this is exactly equal to the function. And likewise, if I take the integral of a derivative function, this is also equal to the function itself, right? So you think of it basically as the integration and derivatives are inverse operations of each other, right? So integral is inverse of derivative. Okay. All right. So why is this important? Well, if I know that d by dt of ct to the n, this is something we learned earlier, is equal to n c to the n t n minus 1, that means that the integral of basically n c to the t minus 1, n minus 1, that's just basically c t to the n plus some constant. I'll call it d. Okay. All right. In other words, basically, that means that basically integral of ct to the n, okay, just writing, just making a substitution there, this is equal to 1 to the n plus 1, ct to the n plus 1 plus some d. It's constant. All right. Okay. All right. So, so for constant, let's see, so let's keep going. For constant A, for the acceleration, right? Okay. A is dv dt, which means v is equal to integral of a dt. Okay. So we know what that is, right? That's just basically at plus a constant. Okay. Now, in order to basically set the constant, we have to know something about the problem initially. So, to set the constant, we need more info. Okay? And that info is usually basically some velocity at some time. Okay? So usually it's some v at some time t initial, right? Okay. Right. So basically, if ti was basically 0, you know what vi is going to be. Then in that case, basically you have basically v as a function of t, right, is equal to at plus vi. Right. That's easy enough. Okay. And so this is basically the same equation that we had in equation 1, right? Vi plus at. So let's do it again. We know v is equal to x dt, right? Which implies that x is equal to the integral of v of t dt. Now I know what v of t is. I plug that in now, right? I plug that in, basically. This is integral of basically vi plus at dt. It's linear and stuff like that. So what you end up getting is basically vi of t plus 1/2 at squared plus now constant again. And basically you need to know x at time t equals 0 is some xi. And in case you know that, then you could write down the entire thing down. Constant becomes xi. Okay. That's 1. That's 2. All right. So that's basically where that mysterious thing came from. All right. Okay. So let's close this section off with one slightly more complex example, right? So, suppose I know the acceleration as a function of time. That's equal to something gnarly, 3t plus 4 meters per second squared. Okay, so I know that. Okay. And now I need to compute v of t and x of t, right, if at t equals 1, v equals 4 meters per second, and x is equal to 5, right? Suppose I know that. So now let's go ahead and do this thing. So v is equal to integral of a dt. That's integral of 3t plus 4 dt. That's just 3 halves t squared plus 4t plus a constant, which I'll call something vi, okay? Which would be v at 0. So now I know v at t equals 1 now is equal to 4. That's that extra piece of information there. That's going to be equal to 3 halves 1 squared plus 4 times 1 plus vi, okay? And so this is 4 is equal to 3 halves plus 4 plus vi. And so 4 plus 4 this side will cancel that out. It'll be 0. Bring the 3 halves that side. vi is equal to minus 3 halves, right? So now I have the complete answer here. v is function of t is equal to minus 3 halves plus 4t plus 3 halves t squared. Okay, that's the first thing. Second thing, I want to find x of t. Okay, let's do that. X of t is the integral of v dt, right? I plug everything in here. This is just going to be minus 3 halves integral plus 4t plus 3 halves t squared. Entire thing squared there. No, entire thing times dt. So now this is just going to be minus 3 halves t plus 2t squared. Okay, that's this piece right there. and then plus 1/2 t cubed. Okay? All right. Plus xi. Okay? And I know that x at time t equals 1 is equal to 5. What's that? So that's going to be minus 3/5, 3/2, sorry, that's this term, plus 2 plus 1/2 plus xi. So let's see, this is 1/2 plus that one, that's minus 1 plus 2 is 1. It's 5, so that means that xi is equal to 4. And so a complete answer is x of t is equal to 4 minus 3/2 t plus 2 t squared plus 1/2 t cubed. All right? And that's it. Okay, that's it for 1D motion for now, right? We'll talk next week about more complicated topics.